Suppose you work in a domain where you have to manage lots of long-running background jobs, such as doing things like transcribing voice calls, or maybe doing big ETL workloads, or maybe you're running really complex financial calculations. One of the things that you might be required to do is to be able to scale your system up on demand, and you want to make sure those long-running jobs that you've already started don't get canceled and then rescheduled onto another node. This is the problem that we're going to try to solve today using Akka.net. We're going to try to build a distributed job execution platform, and we already have a code sample for this, and all the code is open source. But I want to talk a bit about the problem and how we'd go about achieving it. This is something that we built for one of our Petabridge customers who has this type of problem in their domain, and it's modeled after some work I did in the banking sector a number of years ago, also on top of Akka.net. So let's go ahead and dive in. Now, building a distributed job execution platform sounds intimidating, but with Akka.net sort of built-in components, it's actually quite straightforward to deliver. The first thing we're going to do as part of this is we're going to kind of talk a bit about what we need. The first thing is we need to have the ability to distribute work evenly across our worker nodes. This is where a scheduling algorithm is going to come into play. Part of the way that scheduling algorithm is going to work is going to be detecting which nodes are available inside the network and how busy they are. And one of the ways we're going to measure busyness is through a job sizing mechanism. This is where we essentially estimate how complicated or expensive this job is to execute. And that's usually a very fast and pretty low cost function. The other big requirement we're going to have is don't disturb jobs that are already running, even if it's to keep the cluster balanced. This is where some of our customers that came to us with questions, which is they were using Akka.Cluster.Sharding to go ahead and manage these jobs. And that's a great tool for distributing state, but there's a really key lifecycle difference between a sharded entity actor in a platform like Akka.net or Grain in Microsoft Orleans versus a long-running job. And the big difference is that entities tend to live forever, but they're only busy in very short bursts usually. Jobs, on the other hand, have a very short, finite lifespan, but they are intensely busy while that lifespan's running. So you don't want to restart a job in the middle of its lifespan just to try to take advantage of having a full, even distribution of work. That's not how you want to kind of manage it. And then finally, we need to have some recovery mechanisms built in. In the event that a node that was executing jobs fails or shuts down, or in the event that the coordinator, the actor we're going to use to perform the distribution in step one, in the event the coordinator is killed and restarted somewhere else in the cluster, we need to have the ability to survive both of those scenarios, which this code sample does. Now, this is kind of where I got into a little bit of detail about why sharding is not the right solution to this problem. If on node A, we basically have a job that's in progress and it's 60% of the way through being complete. And let's say it takes about 5 minutes for it to execute. The way cluster sharding wants to work is it wants to achieve a perfectly even distribution of shards across the cluster. And that's for a variety of reasons. Probably the most important one being we want to make sure that state isn't highly concentrated in one location on the network, because that's going to end up creating potentially a single point of failure if we end up having to remove that node from the cluster for whatever reasons, like a planned upgrade, for instance. So you can learn more about this by taking a look at our cluster sharding video we did a couple years ago. But the long and the short of it is sharding is just not a good tool for the job. We need something that's a little bit more flexible. And that's what we can build on top of Akka.net actors. So there's a couple of different ways you can distribute work with Akka.net. Cluster sharding we've already talked about. Another tool that's built directly into Akka.Cluster, and you can look at our intro to Akka.Cluster video to learn more about it, are clustered routers. These are basically like little load balancers. They are able to distribute work using a variety of different strategies. So for load balancing, you'd probably want to use round robin. That's sort of your classic load balancing strategy. And what they'll do is they'll scale up the number of different locations they can route messages to as the cluster expands, and they'll shrink those locations as the cluster contracts. Now that's all fine and good, but the cluster router's got a bit of a problem, which is that it's dumb. It's not going to keep track of what was assigned where, and it's not going to try to essentially distribute jobs based on their size either. Every job is going to be treated as identical inside a clustered routing system. And in the event that your environment crashes or reboots, it's not going to be able to keep track of the prioritization of jobs, which ones need to be reassigned, and also it's not going to try to achieve an even distribution of work. They're very basic and very primitive instruments. What we're going to go with instead is a job tracker. This is a custom actor we're going to implement using a tool inside Akka.net, and I don't believe we've done a video for this, called Akka.Cluster singletons. These are actors that there's only one instance of it globally throughout the entire Akka.net cluster. And cluster singletons are really useful in scenarios where trying to break apart a workload and run it in parallel creates more problems than it solves. Schedulers and job trackers are the two classic examples of these. Now, the actor hierarchy we're going to put together here has a few different parts. The parts that we really care about, if I go ahead and grab my pen tool here, the parts that we really care about are these ones down here. This is all the actors that are responsible for basically performing job execution. The other actors on this chart are, some of them are a little bit of niceties for making this demo look really good on screen, but I'll get into them too. The job submitter actor. If you're building, let's say, a multi-tenant system where people can submit jobs for their company or for their organization or whatever, each individual, let's say, job might be submitted by a distinct tenant. That's what the job submitter region is kind of meant to represent. So that way the submitter gets notified about the progress of the jobs that are in flight and about the execution status of those jobs too. So if a job fails or completes successfully, the job submitter actor will get notified about that. And in the event that this job takes a very long time to complete, hours or so, these actors might temporarily get shut down because there's not a lot of updates. And then we will bring them back and recreate them as soon as one of these job executor actors reports on its status. So we have our job tracker actor. This is the one that we're going to spend some time looking at today. A job receiver actor, which is basically just a top-level actor that we create on each node. It's a local actor for this node. That job receiver actor is going to spawn a job executor actor who actually performs the work. In this case, the job executor actor is just using task.delay to simulate work, but you get the idea. And then finally, on the API nodes, this is the web UI that we're creating. We have a job stream supervisor who basically just subscribes to progress updates from each of these job receiver actors and the job tracker actors and uses that to build those really nice progress bar charts we saw up on screen. Essentially, the job stream supervisor just creates some Akka streams that we turn into server-sent events. And we have I think a YouTube short on our channel talking a bit about that technique, which is also fun and good, but not really pertinent to our conversation here today. So the way this workflow is going to run, and if I go and pull up my web browser, we basically have the ability to, and I can go ahead and say Aaron 2 if I want for my submitter. I can go and submit some more jobs. This is basically routing jobs through the execution platform here. So this is all getting registered with the scheduler, and it's going to begin executing these jobs on different nodes. And you can see my distribution of jobs is even. Every single one of these nodes has a 30-unit job. If I want to schedule some 10-unit jobs, it'll go ahead and allocate those as well. So this is the job tracker actor distributing work to some receivers. And once the receiver takes receipt of one of these job execution requests, it'll go ahead and allocate that to a child actor who will execute it and eventually get us up to 100% completion. So that is the basic gist of sort of what the workflow looks like inside the system. So this is what the actor hierarchy looks like. When I submit a job through the UI, we create a job submitter actor. And that job submitter actor is going to basically be the owner who gets notified about that job getting finished. That's going to cause us to submit a job to that cluster singleton, the job tracker actor. We're going to take a look at the code for that actor in just a moment. That job tracker actor's purpose is to essentially find an available job receiver actor on the least busy node and route that job for execution. The job receiver actor will spawn and run a little job executor actor, and the executor actor will begin executing the job and will periodically report its progress to the job tracker. And then eventually it'll report that the job is finished or the job has failed, and the job tracker will indicate that this job is fully finished and will let all the submitter and subscribers know about that. And that's how we're able to update the UI. So this still allows us to have a horizontally scalable design, just like Akka.Cluster.Sharding. But the key difference is that what happens when we bring additional capacity into the network? Well, in that case, we just have new locations for executing jobs, and none of the old in-flight jobs get canceled and rescheduled, which is exactly what we want. We want to avoid turning a 5-minute job into something longer than that because we had to just arbitrarily kill it and then reschedule it, which is what cluster sharding does. So let's take a look at a little bit of source code before we dive into a more extensive demo where we're going to exercise some of the resiliency functionality of this job execution platform. So this is my repository where this code is here, and I'll link to this in the description of the video. This is all open source, licensed under Apache 2. And if I dive down here, this is our JobTracker actor. Now, the most important things to bear in mind about this actor is A, that it's a singleton, so there's only one of them throughout the entire Akka.NET cluster. Then the other is that this actor is persistent. This is how we make sure that our schedule of all the jobs we've assigned can survive this actor either crashing or getting rebalanced or getting killed. And one of the other things this actor will do after it gets killed and restarted is it'll take a look at its schedule and try to figure out if its schedule is stale or not. And it'll go through a little process of contacting all those receiver actors to figure out, hey, does my schedule match all the currently assigned jobs you're processing right now? That way we can kind of deal with anything that finished in the middle of this JobTracker actor basically being recreated. We can go ahead and play catch up. That's what that's designed to do. So if we scroll down here, we basically keep track of, let's say, this is the I've required actor ref. If you've seen our Akka hosting video, this is how we do dependency injection where one actor gets injected into another. So this allows us to communicate with the job submitter actors. And what's going to happen here is we're going to do a little bit of command processing. Now, most of these commands that we have here are all related to basically managing queries for powering that UI. So querying the status of an individual job, getting the list of all available jobs, being able to subscribe the jobs. This is all pretty straightforward, simple code you can go take a look at if you want to. The most important functions are these two right here, handling commands and handling events. Now, if you've looked at our video on Akka.NET application design best practices, this will be very familiar to you, this pattern, where essentially what a command is in the context of, let's say, an event-driven programming grammar. A command is a request to do something and it has to get validated. So if we take a look at our interface here, JobTracker command, we have just, I think, two implementations of it, submit job, cancel job. And this job comes with a job definition. And in the case of the job definition, we've kept it really simple for the time being, a job ID that's unique and a job size. So sizing a job is a really important function, and it's designed to be really cheap to do, usually like a big O of 1 operation, constant time operation. So sizing a job is essentially a way of scaling how much effort is it going to take to complete this job. In the case of, let's say, audio transcription, which is a use case that a lot of Akka.NET customers have if they're running like an IVR system or a customer support data center with Akka.NET, they might go ahead and basically want to transcribe all those audio calls. So the way you'd size that job is how many minutes of audio are there to process. Or if you're doing something like multimedia transcoding, well, the sheer size of the video is not enough to tell the story. You also might need to take a look at the original resolution it was filmed in, or a better proxy for both of those might be the total amount of megabytes of video that need to be transcoded. That would be another example of sizing a job. Or if you're doing something like finance or ETL, extract, transform, load jobs, the number of rows you need to import or analyze might be a good proxy for that. So if you're doing something like a classic banking function you'd use this type of design for would be like asset line management, essentially doing like an end of month report on how well this portfolio of financial instruments has performed relative to its position the month before. You might basically size the job based off the number of individual notes you need to go ahead and compare. So the number of rows of data that might need to be in that job. So this is really important for being able to communicate to the job tracker how busy is the worker node we're going to send this work to going to be once it begins processing this job. And that's going to have an impact on our scheduling decisions that we're about to walk through. So that's what job sizing is all about. Now, if we go back to our source code here, that's the job definition. We have these two commands, submit job, cancel job. If we go to the JobTracker actor, we have this state object right here. And this is another one of these patterns you've seen in some of our YouTube videos before. This state object is basically a C# record. It's meant to be an immutable object, so it's safe to share. But the real reason why we model this state as its own sort of self-contained object is it allows us to test all of these business rules independently from our Akka.NET actor code. It's kind of like being able to decouple your service layer from your ASP.NET Core HTTP layer if you want to. You want to be able to test your business rules in the service layer without having to also do things like mock up HTTP context if you can help it. So that's what this little record does, this job tracker state. And we keep track of all of the different pending jobs that we've accepted but have not yet placed yet. We keep an eye on every single job that is being tracked by our platform, and we keep track of all the available locations in the cluster that are capable of performing jobs. This is essentially a little thin abstraction over some of the built-in data types inside Akka.NET. This is the Akka.NET built-in address, and then I think node status comes from, it's really Akka.Cluster that we're kind of wrapping over, but it keeps track of things like the node's original address, the membership status, whether this node is currently reachable. Membership status is an Akka.Cluster thing. Nodes that are in the process of leaving the cluster, usually because they're being intentionally shut down, you don't want to assign jobs to those. So we include that information here inside the job tracker. And then finally, we keep track of, let's say, the maximum capacity of this node and the total job size. I think the max capacity on this application is set, let me see if I can find it. I think it is set statically through config somewhere in here. I'll have to take a look at it, but I think we have it set to 100 units currently. Now, we have a couple of little utility functions in here that are really useful, like is this node eligible to receive traffic? Do we have capacity to essentially accept this job? And these sort of little decomposition of all these elements makes it really easy for us to understand and program. So do we have capacity to run this job? If the answer is no, then we probably aren't going to be able to go and run it. If we can run this job, does this job exceed our maximum capacity? And if it does, then okay, we're probably going to wait for someone else to schedule it. But in the event that this job is oversized, what we're going to do is wait for a node to basically achieve sort of be zero busyness. And we're going to assign that job to that node, knowing that it's going to max it out for a while. That's sort of how we're going to handle it in this design. And then we have a couple of other little helper functions for dealing with reserving capacity. This is where when you see us queuing up jobs, we're essentially reserving capacity onto that node. Now the capacity reservation here doesn't mean we're executing this right now. It means that the job tracker is intending for this job to go to this node down the road. And then we take a look at our job tracker state. When we receive a submit job request, we have a little function down here where we're going to check to see have we already accepted this job. And if we have, then we'll go ahead and return a little equivalent of like an HTTP 204, basically saying we've already accepted this job and it's already executing. We're not going to run it again. So we kind of deduplicate the job here. But otherwise, we will go ahead and return a decision to accept running this job. And then we will find a home for it somewhere inside this system, which is I think what we're doing down here. We go ahead and we take the original events and then we call place pending jobs. And what we're going to do, this is a fairly simple sort of sorting algorithm. What we're going to do is find the least busy node at this point in time, and we're going to go ahead and assign that job to that node. So the least busy node in this case means whichever node has the most available capacity in the future. So this is counting both the current executing capacity and also the future reserved capacity that's available. So this is not necessarily the most efficient way of distributing work inside the system. There's all sorts of little gap detection measures you could go ahead and add to try to find ways to sneak smaller jobs in while big jobs are waiting to get executed. All sorts of stuff you could do to try to more fully utilize the nodes if you wanted. But this is meant to be a proof of concept that is relatively simple. And so all we're doing here is we basically just grab which nodes are in use. We basically keep track of which jobs are already assigned to which nodes and what the total sizes of all those different, let's say, jobs are for every single node. That's what we're totaling up here. We sort through these and we basically assign them to the node that has the smallest queued size. That's all that we're doing. Now, what gets a little bit more interesting is that when we scale out and we find new capacity on our network, one of the things we're going to do is notice, hey, wait a minute. Do we have some jobs that are queued up and some nodes that have capacity to go and run that right now? Because if we do, maybe we can go ahead and reassign some of these jobs that are queued up on busy nodes to new nodes that are idle. And that's what this little bit of code does here. Now, I'm not going to spend a huge amount of time going through every single line of this function, but I will show you a quick demo of what this sort of scale up looks like and this rebalancing in practice. So let's take a look at that. All right, so what I've got here is a really busy system where I've got 34 jobs queued and 6 are running. All these jobs are like size of 45, essentially. And so you can see they're all being worked on in progress here. Each node can basically run about 2 jobs at a time. What happens if I scale from, I guess we're running 3 worker nodes now. Let's go from 3 to, let's say, 8. So I'm going to go ahead and basically scale up my number of Docker containers here. All right. And those new Akka.NET nodes should all join the network here real shortly. So let's see if that all happens. There we go. And so we went from having like 8 jobs queued on each of these nodes to, let's say, having 2 or 3. And if I scroll down here, a bunch more jobs are all running in parallel now compared to what we used to have before. So that's pretty slick. This means that we're able to go ahead and redistribute all these jobs that were queued up in these 3 nodes got spread out over all these ones. Now, there's still so much work inside the system that we aren't able to go straight to having, let's say, nothing queued at all. We just went and shrank the queue size a bit smaller so some more of these jobs can be executed in parallel on this machine. Now, likewise, one of the things I can also do is scale the system back down again. And all the jobs that were in flight or all the jobs that were queued will get rebalanced back onto the remaining nodes inside the cluster. So I'm going back from 8 nodes to 3 again, just using Docker Compose to kind of control this. All right, there you go. We saw that we had some nodes that were unqueued or maybe only had one thing in the queue. We're back to having 4 queued jobs in each of these nodes again. So this is kind of showing the flexibility of the system to make sure that jobs get redistributed and on scale out and also on scale down. So that's really good. And we take a look through here. We don't have any jobs that have failed to complete, only jobs that are queued and jobs that are running. If I go and scale the system back up again, it'll continue working as scheduled. And so what our code is doing inside the sample here is basically taking advantage of the cluster to go ahead and redistribute our queued up jobs and spread them out across the other nodes. But the other part of it that's more, let's say, convenient here is that the jobs that were already running aren't affected at all when we scale the system up. Contrary, they're actually kept executing happily where they are now in order to help us guarantee that we're able to get as much work done as we can without disrupting any of the current work that was done in flight. The idea being make sure that every job executes in the shortest amount of time possible. That's what I've got for you today. Maybe we'll do a deeper dive on some of the concepts and code from here a little bit later, but I wanted to go ahead and talk through some of the work that we've done for our Akka.NET support customers, which you should go ahead and check out if you're interested. And likewise, introduce you to the idea of using Akka.NET to build work execution platforms if you have this type of long-running background job you need to complete. So that's all from me today. Thanks for your time. Much appreciated. Well, that'll do it for this video. If you found this video useful, please don't forget to check the description to find links to other resources we may have included, so blog posts, GitHub code samples, other videos, so on. And as always, don't forget to like and subscribe and ring the bell for notifications. We'll catch you next time. Thank you very much.